They thought it was a mistake at first. When the Marine Patrol stumbled upon the abandoned Japanese tank half buried in volcanic ash on Iwo Jima, they assumed it was just another disabled Hago or Chiha, the standard light tanks they'd been destroying with 50 caliber machine guns since Saipan. But as they circled the vehicle, brushing away the black sand that caked its hull, they realized this was something entirely different. The turret was mounted in the wrong place, the tracks were unusually wide, and strangest of all, there were two engines, one in the front, one in the rear. The Marines radioed back to headquarters that they'd found something odd, something experimental. What they'd discovered was the Type 5 Shiri, Japan's desperate attempt to build a tank that could actually compete with American armor. It was a machine born from desperation, designed with ambition that far exceeded Japan's industrial capacity, and it represented everything about Japan's war effort itself. Microcosm, brilliant engineering hampered by impossible circumstances, innovation strangled by resource scarcity, and hope crushed by mathematical reality. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The story of the Chiri begins not on Iwo Jima in 1945, but in a series of increasingly desperate meetings at the Japanese Army Technical Bureau, beginning in 1943. By that year, Japanese military planners could no longer ignore what frontline reports had been telling them for months. Their tanks were obsolete, not just outmatched or slightly inferior completely, catastrophically obsolete. The Type 95 Hago, which had seemed so effective in China and Manchuria, was being penetrated by American heavy machine guns. The Type 97 Chiha medium tank, Japan's most numerous armored vehicle, couldn't damage American Sherman tanks, even at point-blank range, while Sherman's 75mm guns could destroy Japanese tanks from over a mile away. At Tarawa in November 1943, Marine Corps Sherman tanks had destroyed Japanese positions with impunity. At Saipan in June 1944, the largest Japanese tank assault of the Pacific War had been annihilated in a single night, with 31 tanks destroyed and hundreds of crew members killed. Intelligence reports from the Battle of Kursk on the Eastern Front, where German and Soviet forces had clashed in the largest tank battle in history, made clear that armor warfare had evolved far beyond what Japan's military had anticipated. The Germans were fielding Tiger tanks with 88mm guns and frontal armor up to 100mm thick. The Soviets countered with 34 tanks, featuring sloped armor that provided effective protection equivalent to 90mm or more. Meanwhile, Japan's newest production tank, the Type 3 Chi-Nu, had only 50mm of frontal armor and a 75mm gun with inferior ballistics to American or European weapons. The mathematics were unforgiving. American factories were producing Sherman tanks at a rate exceeding 1,000 per month across multiple manufacturers. Soviet factories, even after the German invasion had devastated Western Russia, were producing 34 tanks at rates exceeding 1,200 per month. German industry, despite Allied bombing and resource constraints, still managed to produce several hundred tanks monthly. Japan's entire tank production for 1943 was approximately 500 vehicles of all types. The nation that had challenged the world's greatest industrial powers was producing fewer tanks in a year than the United States produced in 2 weeks. But numbers alone didn't capture the full scope of Japan's armor crisis. The technological gap was widening with each passing month. American tanks were getting better. The Sherman 76, with its higher velocity 76mm gun, was entering production. The M26 Pershing heavy tank, mounting a 90mm gun and thick armor, was in development. British forces were fielding the Comet, mounting a high-velocity 77mm gun. Even the Soviets, whose 34 had seemed adequate in 1941, were upgrading to the 34-85 with a more powerful main gun. Japan's newest tank in production, the Chi-Nu, was already obsolete by global standards before the first one rolled off the assembly line. Colonel Tomio Hara, one of Japan's most experienced armor officers, presented a classified report to the Army Technical Bureau in August 1943. Hara had commanded tank units in China and had personally examined destroyed Japanese tanks recovered from Tarawa. His report was devastatingly honest in a military culture that often valued optimism over accuracy. Japanese tanks could not compete with Allied armor in any measurable category. Firepower, protection, mobility, crew comfort, reliability, or maintainability. The gap was so wide that incremental improvements would be meaningless. Japan needed a revolutionary design, a tank that could actually stand toe-to-toe with a Sherman or 34. Anything less would simply result in more dead crews and more destroyed vehicles. The technical requirements Hara outlined seemed almost fantastical given Japan's industrial situation. The new tank would need frontal armor of at least 75 mm, preferably sloped to increase effective thickness. It would need a gun capable of penetrating 60 mm of armor at 1,000 meters, which meant something in the 75 to 88 mm range with high muzzle velocity. It would need to weigh between 30 and 35 tons to balance protection, firepower, and mobility. It would need a crew of at least 4, preferably 5, to distribute the workload that currently overwhelmed Japanese tank commanders. And critically, it would need to be producible in meaningful numbers with Japan's limited industrial capacity and increasingly constrained access to raw materials. The response from the Army Technical Bureau was to authorize development of not one but 2 new medium tank designs. The Type 4 Chito would be an intermediate solution, mounting a long-barreled 75 mm gun and featuring improved armor. The Type 5 Chiri would be the revolutionary design Hara had called for, a true medium tank capable of engaging Allied armor on equal terms. Mitsubishi Heavy Industries received the contract for the Chiri in October 1943. The lead engineer was Asada Shigeo, a veteran tank designer who had worked on earlier Japanese armored vehicles and understood both the theoretical requirements and the practical constraints Japan faced. Shigeo's design team faced an impossible challenge. They needed to create a 30-ton tank in a nation whose industrial infrastructure was optimized for 7-ton light tanks. They needed to source components and materials that were increasingly scarce as American submarines strangled Japan's access to the resource-rich territories in Southeast Asia. They needed to design for mass production in factories that lacked the heavy machinery and tooling needed for large-scale tank manufacturing. And they needed to do all of this while American bombers were beginning to strike at Japan's industrial heartland with increasing frequency and effectiveness. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now back to the story. The design that emerged from Shigeo's team was unconventional by any standard, reflecting both ambitious engineering and desperate improvisation. The Chiri would mount its main turret not in the center of the hull, as was conventional, but toward the rear. This rearward placement was necessary because the tank would have 2 engines, a Mitsubishi Type 100 air-cooled diesel in the front and a BMW aviation engine, license built by Kawasaki, in the rear. The dual-engine configuration wasn't an elegant solution born from careful planning. It was a desperate compromise forced by Japan's inability to develop a single engine powerful enough to move a 37-ton tank at acceptable speeds. The front engine would provide approximately 400 horsepower. The rear engine would add another 550 horsepower. Together, they would give the Chiri enough power to achieve a top speed of 45 kilometers per hour, comparable to Allied medium tanks. But this arrangement created enormous complexity. The 2 engines needed to be synchronized, requiring a sophisticated transmission system that Japan's manufacturers had never built before. The drivetrain had to transmit power from both engines to the front drive sprockets, necessitating a complex system of shafts, gears, and couplings running the length of the hull. The fuel system needed separate tanks for each engine, with the front engine using diesel and the rear engine requiring aviation gasoline. Maintenance would be a nightmare, requiring access to 2 completely different engine types with different fuel requirements, different cooling systems, and different maintenance schedules. The armament was equally ambitious. The main gun would be a 75 mm Type 5 tank gun, a new design with significantly better ballistics than earlier Japanese tank guns. The weapon had a barrel length of 56 calibers, meaning the barrel was 56 times the diameter of the bore, which would give it a muzzle velocity of approximately 2,300 feet per second, with armor-piercing ammunition. This was comparable to the American 75mm M3 gun mounted in Sherman tanks and significantly better than the shorter-barreled 75mm guns in earlier Japanese tanks. But the Chiri's designers went further. They added a 37mm gun in the hull front, operated by a dedicated gunner. This secondary weapon could engage light vehicles and infantry, while the main gun focused on armor threats. Additionally, the tank would mount two 7.7mm machine guns, one coaxial with the main gun in the turret, one in a ball mount beside the hull gun. The four-weapon system reflected Japanese doctrine, emphasizing the tank's role in infantry support, but it also created weight and complexity issues that would plague the design. Armor protection represented the biggest departure from previous Japanese tank design, where the Ha-Go had 12mm of armor and the Chi-Ha had 25mm. The Chi-Ri would have 75mm on the turret front and 50mm on the hull front, both sloped at angles to increase effective thickness. The side armor would be 35mm, and even the rear armor would be 20mm thicker than the frontal armor of Japan's earlier light tanks. The designers understood that armor this thick would make the Chi-Ri too heavy for the lightweight bridges and roads common throughout Japan and its occupied territories. They understood that the thin armor on Japanese tanks had been a death sentence for crews facing Allied weapons. They had examined American tanks captured in the Philippines and Dutch East Indies. They had read intelligence reports about the Sherman's sloped frontal armor and the effectiveness of American armor-piercing ammunition. They knew that anything less than 50mm of effective armor would be inadequate, so they designed for protection, accepting the weight penalty and trusting that the dual-engine configuration would provide adequate mobility. The crew arrangement was another significant departure from Japanese practice. The Chi-Ri would have a 5-man crew, the same as the Sherman. The commander would occupy the turret with a dedicated position, allowing him to focus on situational awareness and tactical command, rather than also serving as gunner and loader. The gunner would operate the main gun using an improved sight with better magnification than earlier Japanese designs. The loader would handle ammunition for the main gun, with access to organized racks holding 75 rounds. The driver would sit in the front left of the hull with improved vision devices. The hull gunner would operate the 37mm gun and coaxial machine gun from the front right position. This division of labor reflected lessons learned from examining Allied tank designs and from the harsh experience of Japanese tank crews who had been overwhelmed by trying to perform too many tasks simultaneously in earlier vehicles. A dedicated commander could maintain situational awareness, communicate with other tanks via radio, which would be standard equipment in the Chi-Ri rather than present in only one vehicle in 4, and make tactical decisions without also trying to aim, fire, and load a gun. A dedicated gunner could focus on target engagement without the distraction of other responsibilities. The workload that had crushed Japanese tank commanders in earlier designs would be distributed across specialized crew positions. The internal layout prioritized crew effectiveness in ways previous Japanese tanks had not. The turret would have a turret basket, a rotating floor suspended from the turret ring that moved with the turret, allowing the commander, gunner, and loader to maintain their positions and access to equipment regardless of turret orientation. Earlier, Japanese tanks lacked this feature, forcing crew members to walk around the inside of the hull as the turret rotated, stepping over drive shafts and equipment while trying to do their jobs. The fighting compartment would provide adequate space for crew members to move, with approximately 150 cubic feet compared to the 50 cubic feet in a Ha-Go turret. Ammunition storage would be organized in racks with proper spacing, rather than loose rounds scattered throughout the crew compartment, as in earlier designs. The commander's position would include a cupola with vision blocks providing all-around observation, similar to Allied tanks. The gunner would have a telescopic sight with magnification and a hand-wheel traverse system that, while not powered like American or German designs, would at least be geared for smooth, controlled movement rather than the crude hand-crank systems in earlier Japanese tanks. By July 1944, Mitsubishi had completed detailed drawings and begun fabricating components for the first prototype. The project moved forward despite increasingly dire strategic circumstances. American forces had captured Saipan, bringing B-29 bombers within range of Tokyo. The Imperial Navy had been crippled at the Battle of the Philippine Sea, losing 3 fleet carriers and hundreds of aircraft. American submarines were sinking Japanese merchant shipping at an unsustainable rate, cutting off access to oil from the Dutch East Indies, rubber from Malaya, and iron ore from various sources. The materials needed to build the Chiri high-grade steel for armor, alloy steel for the gun barrel, brass for ammunition cases, copper for electrical systems, rubber for road wheels were all becoming scarcer. Factory workers were being drafted into the military or diverted to aircraft production and coastal defense construction. Allied bombing raids were disrupting production schedules and destroying machine tools that couldn't be replaced. The entire Japanese economy was collapsing under the weight of blockade, bombardment, and the cumulative strain of years of total war. Yet, the Chiri project continued because there was no alternative. Japan needed better tanks. The invasion of the home islands was inevitable. American forces were island-hopping across the Pacific, and each captured island brought them closer to Japan itself. When the Americans came, Japan would need every defensive advantage it could muster. The first Chiri prototype was completed in May 1945. It was an impressive machine by Japanese standards, representing the pinnacle of the nation's armoured vehicle development. The tank measured 6.3 metres long with the gun forward, 2.87 metres wide, and 2.87 metres tall. It weighed 37 tons fully loaded, 5 times the weight of a Hargo. The armour was thick enough to resist 50 caliber machine gun fire at any range. The weapon that had destroyed dozens of Japanese tanks would be ineffective against the Chiri's frontal armour. The 75mm main gun could, in theory, penetrate the frontal armour of a Sherman at combat ranges, giving Japanese crews a weapon that could actually threaten American tanks. The dual-engine system provided enough power for adequate mobility, at least in testing on level ground. The crew compartment, while still cramped by American standards, was vastly superior to earlier Japanese tanks. For the first time, Japanese tank designers had created a vehicle that could theoretically engage Allied armour without being at a hopeless disadvantage. But the Chiri existed in only one example, and by the time it was completed in May 1945, the strategic situation had deteriorated beyond recovery. American forces had captured Iwo Jima in March after a month of brutal fighting. They had landed on Okinawa in April, beginning a battle that would rage through June and cost both sides staggering casualties. B-29 bombers were burning Japanese cities to ash in firebombing raids that killed hundreds of thousands of comparist civilians. The Soviet Union was massing forces in Manchuria for an invasion that everyone knew was coming. Japan's military was preparing for Operation Ketsugo, the defense of the home islands. But the preparations were increasingly desperate. Beach defenses, kamikaze aircraft, suicide boats, civilian militia armed with bamboo spears. These were the weapons Japan was counting on because it had nothing else. The industrial capacity to mass-produce Chiri tanks simply didn't exist. Mitsubishi estimated that with dedicated effort and assuming no further degradation of Japan's industrial situation, they might be able to produce 15 Chiri tanks per month. That was under ideal conditions that no longer existed. In reality, with American bombing intensifying and raw materials nearly exhausted, production of even 5 tanks per month would be optimistic. The Chiri prototype underwent limited testing at the Arago Proving Grounds. Engineers documented its performance, photographed it extensively, and compiled reports on its capabilities and shortcomings. The dual-engine system worked, but was complex and difficult to maintain. The synchronization between engines was imperfect, causing vibration and stress on the drivetrain. The front engine, using diesel fuel, ran at different temperatures and speeds than the rear aviation engine using gasoline, creating cooling and lubrication challenges. The transmission system, which had to combine power from both engines and deliver it to the front drive sprockets, was heavy and prone to mechanical problems. The armor protection was adequate against most threats the tank would likely face, but it made the vehicle heavy enough that ground pressure became an issue. The Chi-Ri's tracks sank deep into soft ground, and the tank struggled on slopes that Allied tanks could climb easily. The 75mm gun performed well in firing tests, demonstrating acceptable accuracy and penetration against test targets. But the hull-mounted 37mm gun proved difficult to aim and had limited traverse, making it of questionable value. The machine guns functioned adequately but were positioned in ways that made ammunition, supply, and maintenance challenging. The crew accommodations, while better than earlier Japanese tanks, still fell short of Allied standards in terms of vision equipment, communication systems, and ergonomics. Most critically, testing revealed that the Chi-Ri, for all its improvements, was still not quite good enough. It was comparable to a Sherman in some respects: gun performance, mobility on level ground, crew accommodation, but it was inferior in others: reliability, ease of maintenance, vision equipment, armor quality. The Sherman had years of combat development and continuous improvement behind it. By 1945, American factories were producing refined Sherman variants with better guns, improved armor, and enhanced reliability. The Chi-Ri was Japan's first attempt at a true medium tank, and it showed. More importantly, even if the Chi-Ri had been superior to the Sherman in every measurable way, Japan couldn't build enough of them to matter. The United States was producing thousands of tanks per month across multiple models. Japan might produce dozens of Chi-Ri tanks over many months, and only if nothing else went wrong. The strategic mathematics were inexorable. Superior quality cannot overcome overwhelming quantity when the quality gap is narrow and the quantity gap is vast. The Japanese Army Command faced a decision in June 1945 that epitomized the impossible choices confronting the nation in its final months of war. The Chi-Ri prototype existed. It represented years of engineering effort and scarce resources. It demonstrated that Japan could, in theory, design a tank comparable to Allied armor. But a single prototype was militarily meaningless. The question before the command was whether to commit the resources needed for production, knowing those same resources could be used for other purposes: aircraft, coastal guns, ammunition, or the 1,000 other items needed to defend against the coming invasion. The decision became moot when the atomic bombs fell on Hiroshima and Nagasaki in August, followed immediately by the Soviet invasion of Manchuria. Japan surrendered on August 15, 1945, and the Chi-Ri never entered production. The single prototype survived the war, parked at a military facility where American occupation forces discovered it along with other Japanese military equipment. What happened next reveals something profound about how military professionals evaluate equipment and about the respect that exists between adversaries even after bitter conflict. When American tank officers examined the Chi-Ri in the weeks following Japan's surrender, they approached it with genuine curiosity rather than contempt. These were men who had fought across the Pacific, who had seen Japanese tanks destroyed by the dozens at Saipan, Iwo Jima, and Okinawa. They knew firsthand how inferior Japanese armor had been throughout the war, but they also understood engineering challenges and industrial constraints. They could recognize that the Chi-Ri represented something different from the Hago and Chi-Ha tanks they'd encountered in combat. The initial examination took place at the facility where the prototype had been stored. American engineers, accompanied by intelligence officers and combat veterans, walked around the vehicle taking measurements and photographs. They immediately noticed the unusual features: the rear-mounted turret, the obvious presence of 2 engines, the thickness of the armor compared to other Japanese tanks they'd seen. One American officer, a major who had commanded Sherman tanks through the Marshall Islands campaign, later wrote in his report that his first thought upon seeing the Chi-Ri was that it looked like what you'd get if you asked a talented engineer to build a modern tank without giving him adequate resources or industrial capacity. The design was clever in places, showing genuine innovation in solving problems, but it was also clearly compromised by limitations that had nothing to do with engineering skill and everything to do with what Japan could actually manufacture. the Americans arranged to transport the Chi-Ri to the United States for detailed examination at the Aberdeen Proving Ground in Maryland, the same facility where captured German and Italian vehicles were being studied. Getting the 37-ton tank onto a ship and across the Pacific was a logistical challenge, but by November 1945, the Chi-Ri was in Maryland. What followed was one of the most thorough technical evaluations of a foreign tank ever conducted by American military engineers. They stripped the vehicle down to its components, measuring every dimension, testing every system, and documenting every aspect of the design. The armor was tested using both non-destructive methods and by cutting sample sections for metallurgical analysis. The steel quality was good. Japanese metallurgists had done competent work with the materials available to them. The armor plate was face-hardened properly, with a hard outer surface and tougher inner core that would resist cracking under impact. But the thickness variations were inconsistent compared to American or German armor. Some plates were slightly thicker than specified, others slightly thinner, suggesting quality control issues in the manufacturing process. The sloping angles on the frontal armor were well designed, providing increased effective thickness against armor-piercing rounds. The engineers calculated that the 50 millimeters of frontal hull armor, sloped at 60 degrees from vertical, provided effective protection equivalent to approximately 90 millimeters against direct fire, enough to stop most American 75 millimeter armor-piercing rounds at medium ranges. The dual-engine system fascinated and puzzled the American engineers in equal measure. They had never seen this configuration before, and initially, they couldn't understand why the Japanese had chosen it. The complexity was obvious. Two completely different engines requiring different fuels, different maintenance procedures, different cooling systems, all somehow synchronized to drive the tank. As they examined the transmission system that combined power from both engines, the reasoning became clear. Japan didn't have a single engine capable of producing the 900 to 1,000 horsepower needed to move a 37-ton tank at acceptable speeds. Rather than abandon the entire project, Japanese engineers had improvised a solution using two available engines. It was ingenious in its way, but also deeply flawed. The synchronization system was mechanical rather than electronic, relying on geared linkages and clutches to match the engine speeds. In testing, the Americans actually got the Chi-Ri running, which required sourcing both diesel fuel and aviation gasoline. The system worked, but produced noticeable vibration and noise. The two engines didn't run smoothly together. They fought each other constantly, with the transmission components absorbing the stress. The American engineers estimated the transmission would require major maintenance or replacement after perhaps 100 hours of operation, maybe less in combat conditions with rapid acceleration and deceleration. The main gun impressed the Americans more than any other aspect of the Chi-Ri. The 75mm Type 5 gun was a genuinely capable weapon, with ballistics comparable to American and German guns of similar caliber. Test firing at Aberdeen demonstrated that it could penetrate 60 millimeters of armor at 1,000 meters and 90 millimeters at 500 meters using armor-piercing ammunition. These were respectable numbers, sufficient to threaten a Sherman frontally at combat ranges. The gun mount and recoil system were well designed, absorbing the firing forces effectively and allowing rapid follow-up shots. The sight, while simpler than American designs, provided adequate magnification and a clear reticle for aiming. One American gunnery officer noted in his evaluation report that if Japan had fielded this gun in significant numbers earlier in the war, Pacific tank battles would have been considerably more dangerous for American crews. But the gun existed only in this single prototype, and by the time it was perfected, the war was already lost. The hull-mounted 37mm gun received less favorable assessment. The Americans couldn't understand its purpose. It had limited traverse, perhaps 20 degrees to either side, and could only engage targets directly in front of the tank. The gunner had minimal visibility through a small periscope and vision port. The ammunition supply was awkward, with rounds stored in racks that were difficult to reach. The gun itself was the same Type 97 weapon used in earlier Japanese tanks, adequate for its intended role but questionable value as a secondary weapon in a medium tank. American evaluators concluded it was a waste of weight, complexity, and crew member that could have been better used by making the main gun more effective or adding more armor. The crew positions were examined in detail, with American tankers of similar size to Japanese crew members climbing into the Chi-Ri to evaluate habitability and combat effectiveness. Their assessments were mixed. The commander's position was significantly better than in earlier Japanese tanks. The cupola provided all-around vision through periscopes that were adequate, if not exceptional. The commander had space to move and access to radio equipment mounted within easy reach. He could actually command the tank rather than also trying to gun and load. But compared to the Sherman's commander position with its excellent vision, cupola, and comfortable seating, the Chi-Ri's station was cramped and had inferior sight lines. The gunner's position was workable. The seat was basic but functional. The controls for turret traverse and gun elevation were mechanically linked without power assistance, requiring physical effort but responding smoothly. The telescopic sight was simple but clear. The gunner could do his job, though he would tire more quickly than a Sherman gunner with powered controls. The loader had perhaps the most improved position compared to earlier Japanese tanks. The turret basket meant he didn't have to walk around the hull as the turret rotated. Ammunition racks were organized and mostly accessible, though some rounds were stored in locations that would be difficult to reach during combat. The loader could maintain a reasonable rate of fire, estimated at 4 to 6 rounds per minute under combat conditions, slower than a trained Sherman crew, but adequate for the task. The driver and hull gunner positions were more problematic. The driver's station was cramped, with limited space for his legs and minimal headroom. The vision devices were adequate for basic navigation, but inferior to American designs. The controls, steering levers, throttle, gear shift, and brake pedals were laid out reasonably well, but required more physical effort than American tanks with their more refined control systems. The hull gunner beside him had perhaps the worst position in the entire tank. He was squeezed into a small space with his 37mm gun, with minimal ability to move and very limited visibility. Multiple American test subjects climbed into this position and reported it was claustrophobic and would be nearly intolerable during extended operations. One Marine Corps tanker who had fought at Iwo Jima and volunteered to evaluate captured Japanese equipment spent 15 minutes in the hull gunner position and emerged saying he'd rather walk into combat than fight from that station. The testing extended to mobility trials. The Chi-Ri was driven around Aberdeen's test tracks, across various terrain types, and up and down slopes to evaluate its performance. The results were mediocre. On paved roads and firm, level ground, the tank performed adequately, reaching speeds comparable to a Sherman and handling reasonably well. But on soft ground, in mud, or on slopes, the Chi-Ri struggled. The weight was too much for the track width, causing high ground pressure that made the tank sink into soft surfaces. The dual-engine system provided adequate power on level ground but couldn't deliver the low-end torque needed for climbing steep hills or pulling through thick mud. The suspension system, a conventional leaf spring design, was simple and robust, but provided a harsh ride compared to American or German suspension systems. Crew members riding in the tank during tests reported being thrown around violently in rough terrain, making it difficult to maintain situational awareness or work effectively. The transmission problems that engineers had predicted based on examination became obvious during actual operation. After just 20 hours of testing, including only a few hours of hard use cross-country, the transmission began showing signs of wear. Gears were grinding, synchronization between the two engines was becoming inconsistent, and fluid leaks appeared at multiple seals. The Americans concluded that the transmission would require complete overhaul after perhaps 50 hours of use, completely unacceptable for a combat vehicle. Sherman transmissions regularly lasted 500 hours or more between major maintenance, and even German tanks, notorious for mechanical complexity, managed several hundred hours. The Chi-Ri's fundamental design flaw, trying to make two engines work together, created a maintenance burden that would have been impossible to sustain in combat conditions. Supply. Lines would need to carry parts for 2 different engines, 2 different fuel types, and complex transmission components. Maintenance units would need personnel trained on both engine types. Combat units would face constant mechanical problems, requiring skilled technicians to diagnose and repair. The tank might be theoretically capable when it was running, but it would spend more time broken down than operational. The final American assessment, compiled in early 1946 and classified until the 1950s, was respectful but clear. The Chi-Ri represented a genuine attempt by Japanese engineers to create a tank capable of competing with Allied armor. The design showed innovation and problem-solving in the face of severe constraints. The main gun was effective. The armor protection was adequate. The crew layout was a significant improvement over earlier Japanese tanks, but the vehicle was too complex, too difficult to maintain, and not quite good enough to overcome its mechanical limitations. If Japan had somehow fielded Chi-Ri tanks in large numbers in 1944 or even early 1945, they would have made Pacific tank battles more challenging for American forces. Japanese crews would have had a fighting chance instead of certain death, but the tanks still would not have changed the war's outcome because Japan couldn't build them in sufficient numbers, couldn't supply them adequately, and couldn't maintain them in the field. The report concluded with an observation that captured the essential tragedy of Japan's armored warfare program. Japanese tank designers were not incompetent. They understood the principles of armor design. They knew what a modern tank required. But they were trying to build industrial-age weapons with a manufacturing base that was being destroyed by bombing, strangled by blockade, and depleted by years of total war. The Chi-Ri was the best tank Japanese industry could produce under those circumstances, and it wasn't good enough. For the American engineers and officers who examined the Chi-Ri, the experience provided perspective on their own equipment and industrial advantages. They had taken for granted the reliability of Sherman tanks, the availability of spare parts, the redundancy in American supply chains that meant broken tanks were repaired quickly and returned to service. They had assumed their enemies had similar capabilities, just with different equipment. The Chi-Ri revealed how enormous the industrial gap had been. Japan had been fighting with one hand tied behind its back the entire war, trying to compete with nations that possessed 10 times its industrial capacity and access to resources Japan simply didn't have. The question that haunted some American officers was what Japan might have accomplished if the nation had chosen differently in the 1930s. If Japanese military planning had focused on defense rather than expansion, if resources had been husbanded rather than spent on wars in China, if industrial development had been prioritized over military adventurism, could Japan have built an armored force capable of genuine resistance? The Chi-Ri suggested the answer might be yes. The technical knowledge existed. The engineering talent was there. What had been missing was time, resources, and strategic clarity. By the time Japan recognized it needed modern tanks, the war was already lost, and no amount of engineering innovation could overcome the accumulated disadvantages of years of strategic mistakes. The Chi-Ri prototype remained at Aberdeen Proving Ground for several years, occasionally shown to visitors and used as a training aid to teach American officers about foreign armor design. Eventually, it was moved to storage, and later, according to some accounts, scrapped when storage space was needed for more relevant equipment during the Cold War. Unlike some captured Japanese and German vehicles that ended up in museums, the Chi-Ri disappeared from history, surviving only in photographs, technical drawings, and the detailed reports compiled by the engineers who examined it. The tank itself is gone, but what it represented remains relevant. The Chi-Ri was a monument to the limits of innovation in the face of overwhelming material disadvantage. It demonstrated that clever engineering cannot substitute for industrial capacity, that quality cannot always overcome quantity, and that by the time a nation realizes it has been outmatched, the window for correction may have already closed. For Japan, that realization came too late. The Chi-Ri was completed when American forces were already burning Japanese cities and preparing for the final invasion. The experimental tank that might have made a difference if fielded in 1943 existed only as a prototype in 1945, a symbol of what might have been if circumstances had been different, if choices made years earlier had been wiser, if the mathematics of industrial warfare had been less unforgiving. The Marines who first discovered that abandoned Chi-Ri on Iwo Jima who radioed back about the strange tank with 2 engines and unusual design, had stumbled upon more than just an experimental vehicle. They had found evidence of desperation, of a nation throwing everything it had into a last attempt to create weapons that could compete with those of its enemies, knowing even as they built them that it was too late. The story of the Chai-Ri didn't end with its examination at Aberdeen Proving Ground, or even with its eventual disappearance from official records. The tank's legacy lived on in unexpected ways, shaping how military historians understood the Pacific War and how engineers thought about the relationship between innovation and industrial capacity. In the decades following the war, as classified documents were declassified and former Japanese engineers began publishing their wartime experiences, a more complete picture emerged of just how ambitious and how desperate the Chai-Ri project had been. In 1953, a former Mitsubishi engineer named Tomio Hara, not to be confused with Colonel Tomio Hara, who had written the 1943 report, published a technical memoir describing his work on Japanese tank development. Hara had been part of the Chai-Ri design team, and his account provided details that American evaluations had missed. The dual-engine configuration, he revealed, had not been the first choice, or even the second choice. Japanese engineers had initially planned to use a single large diesel engine producing approximately 1,000 horsepower. But that engine existed only on paper. Japan's diesel engine technology, which had been adequate for powering 7-ton light tanks, simply couldn't scale up to produce the power needed for a 37-ton medium tank. The Germans had sold Japan technical data for their Maybach engines, which powered Panther and Tiger tanks, but Japanese industry lacked the precision machining capability and metallurgical expertise to manufacture those engines. The British and Americans certainly weren't going to share their engine technology with a nation they were fighting. So, Japanese engineers had improvised. They surveyed every available engine in Japan's military and civilian inventory that produced more than 300 horsepower. The list was short. The Mitsubishi Type 100 diesel, originally designed for medium tanks, could produce 400 horsepower reliably. The Kawasaki H9 aviation engine, a licensed copy of a BMW design used in fighter aircraft, could produce 550 horsepower. Neither engine alone was sufficient. But perhaps, the engineers reasoned, 2 engines together could work. The concept wasn't entirely unprecedented. Some early tanks had used dual engines, and certain heavy vehicles in civilian use employed multiple power plants. But no one had tried to put 2 fundamentally different engines, one diesel, one gasoline, with different power curves and operating characteristics into a single tank and make them work together seamlessly. The engineering challenges were immense. The 2 engines needed to be mechanically coupled through a transmission that could accept power from both sources, combine it, and deliver it to the drive sprockets without the engines fighting each other or the transmission tearing itself apart. The solution Hara's team developed involved a complex planetary gear system with multiple clutches and a hydraulic coupling that could smooth out the power delivery from the 2 engines. It was an impressive piece of engineering that pushed the boundaries of what Japanese industry could manufacture. It was also a solution that never quite worked properly, as American testing would later confirm. Hara's memoir revealed something else that American evaluators had suspected but couldn't confirm. The Chai-Ri was never intended to be the final design. It was meant to be a stepping stone, a proof of concept that would demonstrate Japan could build a modern medium tank and identify problems that would be solved in subsequent versions. The plan had been to produce 10 to 15 Chai-Ri tanks for field testing with operational units, gather data on their performance and reliability, and then develop an improved Chai-Ri-Kai modified Chai-Ri that would incorporate lessons learned. That improved version would become the standard production model, with perhaps 200 to 300 units built per year starting in 1946. The strategic assumption underlying this plan was that Japan would still be fighting in 1946, that the war would continue long enough for improved tanks to make a difference, and that Japan's industrial situation would somehow stabilize or improve rather than continuing its catastrophic decline. All 3 assumptions proved catastrophically wrong. The war ended in August 1945. Japan's industrial capacity didn't stabilize it. collapsed under the combined weight of American bombing, resource starvation, and the cumulative damage of years of overuse without adequate maintenance. And the timeline that assumed field testing in late 1945, leading to production in 1946, never had any chance of happening because Japan surrendered before a single Chai-ri left the factory. Other former Japanese tank designers and military officers published their own accounts in the 1950s and 60s, and a pattern emerged from their writings. They had all known, at some level, that Japan was losing the industrial war. They had seen the intelligence reports about American production capacity. They had watched as fewer raw materials arrived in Japan, while American submarines sank more and more merchant shipping. They had experienced the bombing raids that disrupted production schedules and destroyed irreplaceable machine tools. But they had continued working on projects like the Chai-ri because stopping felt like surrender, and because there was always the possibility, however remote, that some technical breakthrough might help Japan achieve a negotiated peace rather than total defeat. The Chai-ri represented hope, however irrational, that Japanese engineering could somehow compensate for American industrial might. It couldn't. It never could have. But the engineers who designed it needed to believe they were contributing something valuable, that their work mattered, that they weren't simply rearranging deck chairs on a sinking ship. One particularly poignant account came from a junior engineer who had worked on the Chai-ri's gun mount. He described the moment in June 1945, when the first prototype was completed and underwent its initial test firing. The 75mm gun roared, sending a projectile downrange into a test target. The round penetrated cleanly, punching, through armor plate that represented a Sherman's frontal protection. The engineering team cheered. They had created a weapon that could actually threaten American tanks. Then someone pointed out that even if they could build 100 Chai-ri tanks immediately, which they couldn't, the Americans had thousands of Shermans, with more arriving from factories every day. The cheering stopped. The psychological impact on Japanese tank crews who survived the war and learned about the Chai-ri years later was complex and painful. Many had fought in Hargo and Shiha tanks, experiencing firsthand the terror of being in vehicles that offered no protection against American weapons. They had watched friends and comrades die in tanks that were penetrated by heavy machine gun fire. They had tried to fight Shermans with 37mm guns that bounced harmlessly off American armor, learning that Japanese engineers had designed a tank that might have given them a fighting chance, but that it came too late, and in insufficient numbers reopened old wounds. Some felt betrayed by military leadership that had sent them into battle with inadequate equipment, while resources existed to develop better vehicles. Others felt angry that the Chai-ri project had been prioritized over producing larger numbers of simpler tanks that, while still inferior to American armor, might at least have provided some advantage through numbers. Still, others felt a kind of bitter pride that Japanese engineers had demonstrated the ability to design competitive tanks, even if the nation's industrial situation made production impossible. The most common emotion, though, was a deep sense of wasted talent, wasted resources, wasted lives, all in service of a war that Japan had no realistic chance of winning once American industrial capacity was fully mobilized. For American veterans who had fought against Japanese armor and later learned about the Chai-ri, the revelations produced a different kind of reflection. Many had genuinely believed Japanese tanks were inferior because Japanese engineering was inferior, that the enemy's equipment was primitive because the enemy's technology was primitive. Learning that Japan had designed a tank comparable to the Sherman challenged that assumption. The gap hadn't been one of knowledge or capability. It had been one of resources and industrial capacity. Japanese engineers understood what modern tanks required. They simply lacked the means to build them in meaningful numbers. This realization led some American veterans to think differently about their wartime experiences. The victories they had achieved in tank battles weren't just because American tankers were better trained or more courageous, though training and courage certainly mattered. The victories came because American tankers had better equipment in vastly larger quantities, backed by an industrial system that Japanese couldn't match. War, they came to understand more fully, was as much about factories and supply chains as it was about battlefield tactics and individual heroism. A nation's ability to produce weapons, maintain them, supply them with fuel and ammunition, and replace losses determined outcomes as surely as any general's strategy or soldier's courage. The Chiri also became a case study in military academies and engineering schools as an example of the dangers of technological optimism disconnected from industrial reality. The tank represented what happens when engineers are asked to solve problems without being given adequate resources or realistic timelines. It showed how clever design can create something that works in theory, but fails in practice, because the manufacturing base cannot support it. Military officers studying the Chai-Ri learned to consider not just whether a weapon system was technically superior, but whether it could be produced in sufficient numbers, maintained in field conditions, and supplied with necessary fuel and ammunition. The most sophisticated tank in the world is useless if you can only build 3 of them, and they break down after 50 hours of operation. A simpler, more reliable tank that can be manufactured by the hundreds and maintained by average mechanics is far more valuable, even if it's technically inferior in some specifications. This lesson, learned from Japan's wartime experience, influenced American tank development during the Cold War and beyond. The focus shifted from creating the absolute best tank possible to creating the best tank that could be produced in adequate numbers, maintained easily, and operated by reasonably trained crews. In Japan itself, the Chiri became part of a broader national reckoning with the war years. Japanese society in the decades after surrender struggled to understand how the nation had ended up fighting a war it couldn't win, why military leaders had made such catastrophic strategic decisions, and how a society had been mobilized for total war that consumed hundreds of thousands of lives without achieving any of its stated objectives. The Chiri, along with other weapons like the super battleship Yamato and various experimental aircraft, became symbols of misplaced priorities and wishful thinking masquerading as strategic planning. Resources poured into prestigious projects that produced technically impressive but strategically irrelevant weapons, while basic needs food, medicine, transportation, industrial maintenance were neglected. The pattern repeated across Japan's military-industrial complex. Engineers designed brilliant weapons Japan couldn't build. Officers planned operations Japan couldn't supply. Leaders made promises Japan couldn't keep. And young men died in equipment that offered them no realistic chance of survival against enemies with overwhelming material advantages. The Chai-Ri crystallized all of this into a single 37-ton package: impressive engineering, desperate improvisation, and ultimate futility combined in a tank that arrived too late to matter. Modern historians examining the Chai-Ri have noted parallels between Japan's situation in the 1940s and challenges faced by other nations trying to compete militarily with larger, more industrialized opponents. The core problem is always the same. Innovation and clever engineering can provide advantages in specific situations, but they cannot overcome sustained disadvantages in industrial capacity, resource access, and manufacturing capability. A smaller nation can sometimes achieve temporary technological superiority in narrow areas. Better tanks, better aircraft, better tactics for a particular type of combat, but a larger nation with greater resources can copy, counter, or simply overwhelm those innovations through sheer numbers. The Chai-Ri represented Japan's attempt to achieve technological parity in armored warfare, but even if every aspect of the tank had worked perfectly and production had begun 6 months earlier, it wouldn't have changed the fundamental equation. Japan couldn't outproduce America. It couldn't match American industrial capacity. It couldn't sustain a long war of attrition. The mathematical realities were unforgiving, and no amount of engineering brilliance could change them. The best tank design in the world cannot compensate for being outnumbered 20-1 by tanks that are good enough. The final irony of the Chai-Ri story emerged in the 1970s, when Japanese defense planners, working within the constraints of Japan's post-war constitution that limited military forces to self-defense, began developing modern tanks for the Japanese self-defense forces. These new tanks, the Type 61, followed by the Type 74, and eventually the Type 90, incorporated lessons learned from the failures of World War II. They emphasized reliability and ease of maintenance. They were designed to be manufactured with Japan's actual industrial capabilities rather than aspirational capabilities. They focused on being good enough rather than trying to be the absolute best. And they were developed in peacetime, with adequate budgets, access to global markets for materials and components, and the ability to learn from other nations' tank development programs. The engineers working on these modern tanks sometimes referenced the Chi-Ri, not as a model to emulate, but as a reminder of what happens when ambition exceeds capability and when political leadership makes promises that engineering cannot fulfill. The Chi-Ri had been Japan's attempt to leapfrog from 1930s technology to 1940s technology in a single bound, without the industrial foundation to support that leap. Modern Japanese tank development proceeded incrementally, each design building on lessons learned from its predecessor, each improvement verified through testing rather than assumed through wishful thinking. The physical Chi-Ri prototype may be gone, likely cut up for scrap decades ago when its historical value seemed minimal compared to the need for storage space. But its story remains relevant as a reminder of the complex relationship between technology, industry, and warfare. The tank's unusual design, with its dual engines, rear-mounted turret, and compromised systems, tells us more about the desperation and constraints Japan faced than any official history or strategic analysis could convey. Every unusual feature, every improvised solution, every clever workaround represented a problem that Japanese engineers couldn't solve properly because they lacked the resources to do so. The Chi-Ri was a monument to making do, to trying to accomplish the impossible with inadequate means, to refusing to admit defeat even when defeat was inevitable. For the Marines who first stumbled upon it on Iwo Jima, it was just a strange-looking tank, another piece of enemy equipment to be examined and assessed. They couldn't have known they were looking at the physical embodiment of Japan's wartime struggles, at a machine that represented both the heights of Japanese engineering ingenuity and the depths of Japan's strategic miscalculation. They couldn't have known that this odd tank with two engines would become a historical footnote, that future generations would study not for what it accomplished, which was nothing but for what it revealed about the war, about industrial capacity, about the limits of innovation, and about the terrible costs of fighting wars that cannot be won. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.